Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
Take the numbers 4, 2, 3, and 5. Put a few basic symbols between them and ask 10 people to solve it.
You'd probably get 10 different answers.
Right. Without one invisible set of rules, you might calculate 5,184, 80, or even 96. So today, we're decoding the hidden grammar that prevents that kind of mathematical chaos.
It really is hidden grammar, yeah.
And to tackle this, I'll be playing the inquisitive student today, ready with all the tough questions.
Sounds good. And I'll take on the role of lecturer to guide us through the logic. No chalkboard dust, I promise. Just the underlying architecture of how we, universally agree on what numbers mean.
Perfect. So our material today comes exactly from section 3.3 of chapter 3 from Contemporary Mathematics.
The great text.
It is. But section 3.3 starts with a deliberately confusing sentence that legitimately made me think I was losing my mind.
Oh, I know the one.
Yeah, let me read it. It says, calculates else, sure, someone be rules explicit. We, what that need make. We to dead end them would be calculate to calculate it first.
It's completely jarring.
Right. Total nonsense.
But it proves the textbook's point perfectly. You can have a collection of perfectly valid English words, but if you completely strip away the syntax and the word order, you are left with pure gibberish.
Yeah.
You need a strict, agreed-upon structure to convey actual meaning.
Which maps directly onto math. Like if we don't have a strict order of operations, arithmetic completely falls apart.
Exactly.
Taking that wild example from the textbook, it's 4 times 2 squared plus 3 plus 5 squared.
Right.
If you just randomly guess how to group those operations, you end up with those wildly different answers I mentioned earlier.
Total chaos.
Yeah, but apply the syntax, and there is only one single correct answer, which is 44.
Right, and the foundational mechanism that prevents that chaos is EMDAS.
EMDAS.
Yeah, exponents, multiplication and division, addition and subtraction. It's the universal convention ensuring everyone on Earth looking at that expression arrives at 44.
Okay, wait, let's unpack that, because we all learned EMDAS or PEMDAS in grade school, but there's a common trap here.
Oh, definitely.
Since M comes before D in M&DS, the assumption is that you always multiply before you divide, right?
See, that's a really widespread misconception. Multiplication doesn't automatically trump division.
It doesn't.
No. In this hierarchy, they actually hold the exact same position. The rule is simply that you move from left to right across the equation, just executing whichever operation you hit first.
Oh, right. Because under the hood, they're fundamentally the same thing. Division is really just multiplying by the reciprocal.
Exactly. They are two sides of the same coin.
Okay, that makes sense.
And that same left-to-right sweep applies to addition and subtraction, because subtracting is just adding a negative number.
Gotcha.
They carry equal weight, so the default state is always just moving left to right.
Okay, so left to right is our linear default. But, math isn't always linear. What if the logic requires us to force a detour?
How do you mean?
Like, say I absolutely need to add 2 numbers together before doing the multiplication.
Okay. That's where I bring in the P for parentheses, which expands EMDAS into PEMDAS.
Right, PEMDAS.
Parentheses are the architectural tool used to explicitly break that standard order. So if you need to multiply 4 and 7 before squaring them, you bracket the 4 times 7 inside parentheses and put the exponent on the outside.
So it's open parenthesis, 4 times 7, close parenthesis, squared.
Exactly.
It's essentially a localized override command for the standard syntax.
That's a really great way to look at it. And when you get into highly complex equations with nested parentheses, parentheses inside parentheses, the system scales perfectly.
You just work from the inside out.
Yep. You simply start with the innermost set and resolve your way outward to the surface.
Wow. Okay, so zooming out, the real takeaway for you listening isn't just a refresher on grade school math. It's realizing that the order of operations isn't arbitrary torture.
No, not at all.
It's a vital universal syntax. It's what guarantees that a formula calculated in Tokyo yields the exact same result when calculated in Toronto.
It's the bedrock of logical agreement. And, thinking back to that scrambled, gibberish sentence we started with, it does make you wonder.
Wonder what?
Well, since math relies on this strict, universally accepted syntax to prevent chaos, what would an order of operations look like for everyday human conversations?
Oh, wow. Imagine a structured syntax that could completely eliminate misunderstandings when we speak.
It'd change everything.
It really would. That's a fascinating thought to mull over until our next deep dive.